Hi, welcome again to this Mohr circle exercise. As we mentioned, we were discussing until now what is the planar case of Mohr circle, and that was done in order to introduce a 3D case. So that is important because everything we did with the planar case is going to be in somehow repeated to the third 3D case, meaning that that's going to allow us to understand what was the procedure or how this 3D Morse circle is constructed. But before that, let's make an example about Morse circle. So we have this case where we have determined in our structure or any body part that this planar element is affected by the following stresses. So we have stresses in the x direction, 80 megapascal, normal stress in the y direction, 40 megapascals, and then we have a shear stress of 30 megapascals. If I bring this planar element, I know that I'm going to, the simplistic way to write this planar element or stresses applied to the planar element is just by writing this or by drawing these two planar stresses coming out of the surface in this case, and then this shear stress. This shear stress, these are going to be the same because of the reciprocity of shear stresses as we see in the 3D case or in the complex case. But which value of this corresponds to which? So we have first the x direction that we have taken on all of our exercises as the horizontal axis, and then we have the y-axis. We have been using the vertical axis to represent this y-axis. So meaning that 80 megapascals are represented as a normal stress coming out of this face here, so oriented along the vertical axis. Then we have the sigma y 40 megapascals in the vertical axis, and the remaining one, you already can kind of figured out that this is going to be the shear stress. So this is the way how these three written stresses can be represented in the planar case. Pretty simple. We haven't done this, but this is a very simple way to represent it. And whenever you find these kind of stresses written in this way, and you want to know how they are written, graphically, remember to respect the positive convention that we have been dealing with in the past. Although for more circle, there's going to be a kind of a tweak. So we're going to represent, or we're going to consider positive certain stresses that, or kind of, it's going to be a little bit kind of counterintuitive with respect to the assumption we did to represent positive shear and normal stresses in the past. Anyway, let's continue. Let's move this out of the way, and let's bring a coordinate system that would allow us to draw our Morse circle. And here is where the usefulness of a Morse circle comes into place. We are going to understand that. So until now, we haven't written any formula or any equation to calculate, our principal stresses, which is, what is being asked in this problem. So we need to calculate principal stresses, maximum shear stresses, and associated normal stresses, and their kind of direction or orientation with respect to the original orientation. So in this case, how to draw the Morse circle. Even though you know how to do this, I believe this is a good practice. First, let's consider this pair here. So this is basically the normal stress in the x direction and the shear stress. What we will do is that we will plot this point into this set of axes, kind of the normal stress axis and the shear stress axis correspondingly. So this is going to bring this point, and this point is going to be, or is going to have these Cartesian coordinates, 80 in the normal stress and minus 30 in the shear stress. And minus 30 because in Morse representation, we're considering that shear stress that make the planar element rotate anti-clockwise, they are considered negative for the Morse case. In our case, let's remember that our principle used This is considered a positive shear stress. However, for the Mohr's case, uh, whichever shear stress that makes our element rotate anti-clockwise is going to be negative, and those that make our element rotate clockwise, they're going to be positive. So this is a negative shear stress for the Mohr circle, and this is a positive shear stress in the Mohr circle case. We have this now, and then let's consider this other pair. So let's plot this other point, and this is going to be, say, this one here. Again, positive normal stress, positive shear stress. Normal stresses are positive, same as our main convention or original convention. So having this point, what we will do now is to draw a line between these 2 points, and wherever this line cuts the normal stress axis, it's going to be the center of my Morse circle. In this case, because of the configuration. So if you have noticed this, according to the scale, each division is equivalent to 20 units. So meaning this is 20, 40, 60, and 80. So the center of the Morse circle is in the kind of it has a value of 60 in the normal stress axis. And after having these 2 points, I can draw, sorry about that, I can draw my Morse circle here. This Morse circle kind of has a radius represented by the distance between the point and the center. And we said that the center was going to be this, let's say, 60, and this 60, basically, if you want to use a formula to calculate the center of the Mohr circle, it would be the average of the normal stresses applied to the planar element. So 40 plus 80 divided by 2 is going to give me 60, and that's the value of the center of the Mohr circle here. Great. Now, wherever this circle cuts the normal axis, or normal stress axis, is going to tell us what are the principal stresses. Principal stresses are those maximum normal stresses that we can find when orienting my planar element with different angle from the original one. So you see that in this case, I have determined the center of the Mohr circle just by looking at the scale. So if I have a proper scaled graph, I can know, okay, this is the center of the Mohr circle. Then I know where it cuts. The normal axis is going to produce, or it's going to give me the principal stresses, meaning that if I have, again, a properly scaled axis, I could read directly from the chart what are the values of the principal stresses here. And for this, we don't need any formula, and this is the beauty of a Morse circle, because without doing any calculation, you can extract where are these principal stresses in here. However, we saw in the previous lessons that the value of these stresses is represented by this formula here. And if you take a look at the formula, you are going to see that the first term here represents the center of the circle, and that is this one here. And the second term here represents the radius of the circle, meaning that if I add the center plus the radius, it's going to get me to the first principal stress. And if I subtract, the radius from the center of the circle, it's going to give me the second principal stress. It's pretty straightforward. And remember that we had to do a lot of manipulation and derivations, mathematical derivations, to get to this formula from the equilibrium of a planar case, of a planar element. Then having this, let's move this away. And okay, let's move it a little bit more. It's better here. Then we have another important term. So wherever the maximum of the circle reaches kind of in the vertical direction, it's going to be the maximum shear stress. And the shear stress is going to be represented by the radius of the circle, meaning that it is kind of equivalent to this part here, Also, it is going to be equivalent to subtracting the principal stresses and dividing them by 2. So this is going to give me the three principal magnitudes that are being asked. What are the principal stresses and what's the maximum shear stress? And actually, we know the third or the fourth term being asked, which is the associated normal stress, with the shear stress. We will see that in the end. Why am I saying this? So let me represent it better here. So this is the kind of maximum shear stress. So we have principal stresses and maximum shear stress. All right. So let's move this. Let's make some numerical calculation of this. We have that for the normal stresses, I just plug in all the values, known values. These are coming from the planar case or planar element. And actually, these are the same values written here. And this is going to give me the following. So we're going to have that the first principal stress is going to be 96 megapascals, and the second principal stress is going to be around 24 megapascals here, or 2395 and 96.5 megapascals. For the case of the maximum shear stress, as I mentioned, it could be represented as the radius of the circle, so I could use this formula here, or it could be represented as the subtraction of the principal stresses and their division by 2, and that's going to give me 36 plus minus 36.05, meaning that we have a maximum positive shear stress and we have a minimum positive shear stress 180 degrees apart in Mohrs circle angle. Great. So what else we have? Something, I believe well, let's write in there. Let's write the values there. So we have sigma 1 principal stress, we have sigma 2 the second principal stress, and we have the maximum shear stress here. Nice. Another value that we need to remember is this one. So let's take this value here, because besides knowing what are the values of these stresses, we have to know how do I need to orient my planar element to get to these stresses, to get to the maximum principal or the principal stresses, and to get to the shear stresses. And for that, I need this relationship, because this is the kind of the orientation, the initial orientation of my axis. And then if I want to get from this point to this point, I have to rotate or orient it, my element following this angle here. So let me kind of try to write it better this time. So it would be something like this. So let's remember that the coordinates of this point was 80, comma, minus 30. But if we have 80 here, that was the coordinate in the normal stress axis, but I knew that the center of the circle was 60, then this side is going to be 20, and this kind of vertical length is going to be 30. So these two values are going to allow me to calculate this 2 theta p prime, which was also stated in our kind of the derivation of our formulas. And this is going to be how much I need to orient my element to get to have the principal stresses. And then if I make the use of the tangent of the angle, taking into account these two values here, I'm going to find out that in Mohrs circle angle, I would have to orient my element at an extra 56.30 degrees to get to have the principal stresses. Now we know that we have two principal stresses and they are 180 degrees apart from each other. So by knowing the first direction, I can know the second direction right away just by adding these 180 degrees in Mohrs circle angles. So I'm repeating this Mohrs circle angle because the angles represented in the Mohr circle are kind of are the double of what is represented in reality, and we will see that. Nice. Now, what we have here is that in reality, what I physically would have to orient or rotate my element is to get to the first principal stress is, uh, 22.15. So this is a typo here. This should be just, theta prime, not 2 primes. So I will correct this. And the second one, or the orientation of the second principal stress, is going to be at this angle in the physical quantities. Then if we want to know where the maximum stress is going to be located, we know that is in this vertical line here, and that's going to be kind of at a, how to put it, as a distance in Mohrs circle, let's say quantities, is going to be by pi. So from the orientation where I get my maximum or my principal stress, if I add 90 degrees in Mohr circles angle, then I will get the orientation of the maximum shear stress, let's say, situation. So in this case, as I'm talking now in physical quantities, I already corrected this. What it is, so if I add 45 degrees to this value, I will get the position of the maximum shear stress, and then the other axis where the negative shear stress is located is going to be located at a 45 degrees from this angle here. Great. Now we're approaching the final solution of this. So if I rearrange this and then I would like to plot the solutions I gotten, so I know what are the magnitudes of the principal stresses. I know what is the magnitude of the shear stress, in this case, well, plus minus. I know their orientation now in physical quantities. So let me bring a kind of the normal or the planar element I had in the beginning. So to represent where my principal stresses are going to be occurring, so I need to rotate this planar element to a certain, let's say, angle. In this case, we said it was 28.15, not from 5 here. So another mistake here. Then if I draw my element here, I know that in this direction, I will have my sigma 1, my first principal stress, and 90 degrees from it, I will have my sigma 2, which is my second principal stress. For the case of the shear stress, it's going to be 45 degrees from this line here, or kind of together it would be 72.15 degrees here. And if I draw my element here, I will have the maximum shear stress. So in the situation where I have only principal stress, or where I find my principal stresses, there is not going to be any shear stress at all in this situation. However, when I come and I represent, or I find what's the orientation of the maximum shear stresses are not going to be alone there. They're going to be accompanied by a set of normal stresses. And the value of these normal stresses is going to be represented by the center of this Mohr circle. And let's remember that it was 60. Now, what we have here is the solution to our problem. So we were asked which were the values of the principal stresses, maximum shear stress, and an associated normal stress to the maximum shear stress. So I have here the the principal stresses with orientation included. And in this case here, I have the maximum shear stress with associated normal stresses and orientation included. Now, in this case, you find what is let's say the load situation that doesn't, let's say, help you at all. And the meaning we were doing all this calculation or using Mohr circle is because we wanted to know from this state of stress what were the maximum stresses I could find, meaning principal stresses or maximum normal stresses and maximum shear stress. Because by using these maximum values, let's say that in this case, it was said that my planar representation had a maximum normal stress of 80 megapascals. In this case, I found out that there was an orientation where the maximum stress was 96 megapascals. And in this case, these are the values that I need to use to kind of employ my failure theories or employ in my failure theories. So to assess if the part would break or would kind of pass this yield limit or yield limit of the material. And I would understand if the material would break or the material would deform to a certain extent that is not longer, let's say, usable per se. So this is the final um, uh, solution, how it should be presented. I had a small kind of typos here regarding some measures, but I will correct them in the written version. But well, this is the kind of the end of the example I wanted to present to you. Next, the next video will present to you now the 3D construction of the Mohr circle. And we're going to jump into the construction of the Mohr circle. We won't go through the phases of deriving each one of the quantities, even though we already did that. But we will draw, or I will show you how to draw the Mohr circle for a three-dimensional state of stress. Thanks for watching.